show you just a little bit about the Jacobian of a function. Because I bet you didn't see this in Calculus 3, because it's not really canon, let's say, for Calculus 3. But here's the deal. If you have a function, and that's actually a map from Rn to Rm, all right? So this would take a n-dimensional input, and it would output an m-dimensional output. This is a lot of different things, right? Like there's tons of different cases here. Just to, if you put n equals to 1 and m being whatever, that's a space curve. If you put n equals to 2 and m equals to 1, that's the kind of function we study in Calculus 3, like f of xy. So it's got space curves, it's got functions of 2 variables, it's got functions of 3 variables. If you put n and m both equal to 1, it's just a function of 1 variable. I mean, this has tons of different cases in it. All right. Then the Jacobian of f is equal to partial f, partial x1, partial f, partial x2, partial f, partial xn. And here, I mean the partial, this is a m by n matrix. So these are actually m vectors. It's an m vector. And by that, I don't mean like m vector in the sense of wedge products. I mean, it has m components. See, that's unfortunate. I used a 2 vector in a rather different sense earlier today, didn't I? That is not the same meaning. I mean, m components tall.
So what are the lines representing?
Oh, that's just concatenation. That means just it's this, then that, then that. Those are just decoration. They're decorative.
Just like a comma?
Yeah, like a comma. I think of them as glue and bars. I don't know, whatever you want. I don't know what the name of the... you could put commas there if you want, sure. But you'd be wrong. I'm just joking. So this is an m by n matrix. M as in mommy, n as in nanu, as we discussed. And flippity floppity, you could also write this as a stack of gradient vectors. This is like the gradient of the first component function, the gradient of the second component function, and so forth and so on. Gradient of the nth component, rather the mth component function, and you can write it like that. If you're thinking of gradients as row vectors. If you're not thinking of gradients as row vectors, if you think of gradient as a column vector, then I got to put some transposes there, right? And since I usually do think of gradient as a column vector, I owe you transposes here, I guess. Fine. If I hadn't told you about the transpose, you probably wouldn't have cared. Whatever. So this is the Jacobian matrix of a map. And the Jacobian matrix of a map completely tells you how to linearize the map. It's the generalization of the slope of a function. This matrix is the generalized slope in some sense. So, essentially the result is this. F of, let's say, P plus H is approximately equal to f of P. Well, I can make this equals. This is equal to f of P plus the Jacobian of f evaluated at the point P times the vector H plus eta sub f of H, where this error term, eta sub f of H, goes to 0 as H goes to 0. But it's more than that. It's that over, you can even divide by the norm of H. Excuse me. I also am using capital H and lowercase h. They should all be lowercase h's. My apologies. So sorry. So what this formula says is that the value of the function at p plus h is just the value of the function at p plus the Jacobian matrix times h. That is the linearization of the function. This right here is the so-called linearization of f at p. Hey, let's do an example. Let's make this less abstract. I'll do f of x comma y equal to, let's say, xy, x plus y, x squared. So you got to understand my silly notation. When I write open parentheses like this is my sneaky hidden notation for column vectors. So this actually, if I want to write it, is literally this. So the Jacobian of f here is a 3 by 2 matrix because this is a function from R2 to R3. All right, so great. What actually goes there? What's partial derivative with respect to x? It's y, 1, 2x. So you can see why I put the bar in, just for the sake of, I mean, you don't have to put the bar in, but it can be helpful to distinguish the columns. You can put dots if you like. I mean, it's really just bookkeeping, you know? It's all good. How about partial f, partial y? Well, that's x, 1, and what? Very good. So the linearization, so if we pick up, that's the Jacobian matrix. And so, you know, this is a nonlinear function, right? Suppose you want to linearize it at where? You guys pick a point. No, I'm not going to let you pick a point. You'll give me something weird like pi. Let's choose p equal to, make something that's a little bit distinct so you can tell. How about 1, 2? 1, 2 is a nice point. So notice that, so if we were to look at f of 1 plus, let's say, little h, I'll say find h1, 2 plus h2, you'll forgive me, I'm writing subscripts, that should be equal to, well, it's approximately equal to the linearization of this f at the point P, right? Acting on h1, h2. So that would be equal to f of p plus the Jacobian of f at p times the two-component vector h1, h2. Now, specifically, that is, all right, so I said p was what, 1, 2? F of p is what? It's 2, 3, 4. No, 2, 3 what? X equal to 1, y equal to 2. So 2, 3, 1. 2, 3, 1. That's f of p. 2, 3, 1. What's the Jacobian of f at p? X equal to 1, y equal to 2. So I get 2, 1, 2. And x was what? 1, 1, 1, 0. So there you go. I'll rewrite it in the other notation. This is 2 plus 2h1 plus h2, comma, 3 plus h1 plus h2, comma, 1 plus 2h1. That is the best linear approximation to this nonlinear function at the point 1, comma 2. And that's how you do it. You calculate the Jacobian matrix, you plug in the point, and you basically do the tangent line thing from calculus 1. It's just now you got a matrix and a vector as opposed to a number.
Can you do the math, like, just like, talk about it really fast?
This step?
Yeah, just like.
So what I was doing was this column vector times that gives me 2h1 plus h2 for the top component, which is this. And then h1 times that gives me h1 plus h2 on the second component, which goes here. And then this times this gives me 2h1, which gives me that 2h1 over here. This 2, 3, 1 is just this 2, this 3, this 1. Yeah. So you, I plugged in this point up in here because this is the Jacobian of f evaluated at p. So I plug in the point 1, 2 into here. So y equals 2, x is 1, 1 is 1, 1 is 1, 2x, 2 times 1 is 2. Now, you guys remember in Calc 1, we either use the h formalism or the x minus a formalism, right? So another way you could do this would be like, you could talk about the linearization of f at p at like x comma y. And if you did that, you instead of having the h1 and h2 are replaced with what? h1 is like x minus 1. And h2 would be y minus 2. I'm just rewriting it in terms of x and y as opposed to h1 and h2. The point is x is equal to at 1 plus h1, and y is equal to 2 plus h2. So if you wanted to, you could write the linearization as a function of x and y rather than h1 and h2. It might be useful to have the linearization as a function of the Cartesian coordinates x and y as opposed to these like parameters h1 and h2, which I just introduced. I can never make up my mind on this, whether to talk to students about the x's or the h's. But so this is a pretty cut and dried calculation. You take the map, you calculate the Jacobian matrix, and then you plug in the point. That's the linearization. And this is the best possible linearization in the sense that it minimizes a certain difference with respect to, like, basically the definition is this, guys. Definition, you want f of p plus h minus f of p minus the differential at p of f of h. That divided by norm of h, the limit as h goes to 0 of this equal to 0, what I just wrote. This is the so-called Frechet quotient. And you might not have ever thought about this, but if you wanted to define differentiability for a mapping, this is how you do it. Differentiability for a mapping, and so, okay, my bad. I've kind of used this notation in a different sense, right? And so maybe I shouldn't do that here. Maybe I should have a different, let me put a tilde over this or something, because I'm thinking of this as being the concrete differential in the sense of this is here the dpf is actually, I'll say dpf tilde is literally a map from R and Rm in this context. So this, I'm going to call it tilde, the formula. And if you take a course in advanced calculus, you'll prove that this dpf tilde acting on H is exactly equal to the Jacobian of F evaluated at P acting on H. So this d tilde, which I'm using just a temporary notation because we're not going to talk about it that long. I'm just talking about it long enough to confuse you. Sorry, I try to behave. The dpf tilde is the differential, in the sense of advanced calculus, of the mapping. It is the best linear approximation to the change in the function, which is this, at the point. It is very much akin to the limit quotient definition for derivative. However, notice that there's a big difference. This is an implicit definition. There's no formula. It's not like dy dx equals something, or f prime of p equals something. It's all wrapped up in this so-called Fréchet quotient. But when you work through the theory of this, you can prove that if this limit exists for a function at a point, then you can calculate partial derivatives. And you can use those partial derivatives to, this is a lie what I just said. Actually, we need more. We need not only that this differential exists, we actually need it's continuous. So if, I'm getting the story all messed up. It's complicated. So it turns out that if you have all the partial derivatives existing, right, it's possible for all the partial derivatives of the map to exist, and yet for this quotient, this limiting quotient to fail, because partial derivatives are based on just one-dimensional data. They're based on the change of the function along coordinate directions. For this to exist, this is a multivariate limit. So that's a stronger kind of condition. You need the partial derivatives in the coordinate directions to be nicely linked in some way. And one simple way to do that is to insist on what's called continuous differentiability. Continuous differentiability is when the derivatives not only exist, but they're continuously so. That means that you can kind of weave them together to make the big d tilde, as I'm calling it. And the way you do it is the matrix of this linear transformation is the Jacobian. So anyway, this is the story of advanced calculus. I spent like a month in advanced calculus doing this, all right? Okay, that's not true. 2 weeks in advanced calculus doing this. And so this is the general story of like, how do you generalize tangent lines or surfaces, like the tangent plane? Y equal to the linear, like pair of coordinates equal to the linearization of f input. That's the generalization of the equation to the tangent line or tangent plane. This is a linearization of a multivariate function. So, but none of this does what? None of this involves this new madcap formulation of tangent spaces in terms of derivatives, right? Right, but there should be an analog in the world of abstract tangent spaces to this concept of a linearization, right? And that's actually what we're doing next, is the push forward. The push forward is this idea. The push forward essentially is this d tilde f done in terms of the derivatives instead of, well, here, these are just concrete vectors. But just like everything else, when push comes to shove, our push forward, which I'm about to describe and define, it's just going to be built from the Jacobian matrix of the function that we're pushing things forward by. Let me talk a little bit more, let me give you kind of a big picture of what the push forward's about. Because I think that it's helpful to have some pictures. I should even really leave this up because we can sort of use, well, I better not. Okay, so push forward. That's not H. What is wrong with me? Oh, I skipped straight from finishing writing push to starting writing forward. So as you can see, I need to find a way to bring more coffee to school. And so let me just kind of like be a little bit kind of big picture. So we have some space M, right? Well, actually, let me be slightly less big picture. We have R N, we have R M. We have a function that goes from here to here called f. So the reason it's called a push forward is if you take a vector over here, Vp, an element of, say, the tangent space at P to Rn, then the push forward of Vp should be an element of the tangent space at f of P of Rm. So it's kind of what it sounds like. Like the push forward pushes tangent vectors in the domain of the function over to corresponding tangent vectors in the range of the function. It's a push forward. Now, if you take a just kind of a bird's eye look at this, that's also what's going on over here if you just ignore the f of p term, right? Like, check it out. This Jacobian of f is doing what? It's taking a two-component vector, h1, h2, in the domain, and it's pushing it over to a, see, it's unfortunate that I've written the calculation this way. It's pushing it over, I'll write it up here. So you're taking 2, 1, 1, 1, 2, 0, h1, h2, and it's going to what? It's going to 2h1 plus h2, h1 plus h2. I'm a victim of my own not writing enough down detail in the last one. And then 2h1, right? In fact, this is what the push forward is going to do. So for this example, I'll show you the push forward. The push forward, right, of h1 partial partial x1 plus h2 partial partial x2. I guess I should, I really should be writing those subscripts up. I just, fine. I don't know why it's just bothering me to write them there. I'm an idiot. X2. Maybe, do you care if I use x1 and x2? Do you want me to use x and y? Does it matter? It's fine, okay. This is equal to, what's it equal to? 2 h1 plus h2 partial partial y1 plus h1 plus h2 partial partial y2 plus 2h1 partial partial y3. And here I'm using the system of notation. F is a mapping from R with coordinates x1, x2 to R2, right? R3 with coordinates y1, y2, y3.
Why do partial y?
Because I'm using y1, y2, y3 for the coordinates in the range. Now, you could do like a push forward of the space onto itself. Like you could do that also. So what what are these here exactly? You know? I mean, what with these parenthetical terms that I wrote down, you know where they came from because you saw my previous example. But how do we define that in general? Like, how do you define the push forward of a vector field in general? All right. So we should look at that, and I'm going to use the projector here. Hopefully, it'll work. Uh-huh. I'm waiting for that to warm up. Let me see if I can scribble the definition down. There's a couple of motivating examples in the notes, and then I finally get around to giving the definition of the push forward. And I also call the push forward the differential. I mean, it's the abstract differential, if you will. I mean, in advanced calculus, I think about a differential taking column vectors to column vectors. It's a mapping from Rm to Rn, or Rn to Rm, depending on how I labeled it. But the differential in differential geometry is mapping derivations to derivations. It's mapping derivatives to derivatives, according to our... Oh, no. That's right. We never got this to work, did we? Full screen. I'm gonna save it on the desktop, and then I'm trying to open it with Adobe System Viewer. I don't know what the System Viewer is. I'll try it out, whatever that is. It doesn't have Microsoft Edge. Go be useless somewhere else. Let me try open with Adobe. Maybe it'll let me. At least I know where the full screen is in Adobe, you know? Well, it's full screen on this monitor up here. Yeah, it's not helpful.
Maybe if you just drag it over, it'll just fix itself.
Maybe. Let me try display settings here. If it let me duplicate, that would be awesome. You know? No, usually it has duplicate, you know? Well, all right, get over there. Get. All right, I give up. As I said, next week we will be in a different room. I've had it with this one. Yes, power off, please. Thank you. I'm sorry about that, guys. All right, so let me log out. I want to log out. Sign out. There we go. I told that to turn off, didn't I? It's a bad actor. It won't listen. It won't listen, will it? All right, let's see if we can make sense of this. So as much as I'd love to project the motivational examples in the notes, like those, I actually, so the what the motivational examples in the notes do is they take a curve and they calculate the velocity of the curve, and then they calculate the velocity of the curve composed with the map, and then compare them and see how the map, the composition of the map with the curve compares to the velocity of the curve. And that sort of motivates this push forward, which will relate these two things. So you can define the push forward in terms of composition of the map with a curve and how the velocity filters through, or you can be sort of more heavy-handed and give a formula for it, which is what I'll do here in a second. And so like this is not, certainly not the most beautiful way to do it, but it is nevertheless a way. And so what I do is I suppose that we have a function from Rn to Rm, differentiable at P. I take a vector in the domain, and I take coordinates in the so notation here. Let me set up the notation. F is a mapping from Rn to Rm, and I'm using coordinates y1, y2, ym for there. And so I want to let x be a big X be an element of the tangent space at P to M, right? What does that mean in terms of like a formula? That means that x is actually equal to the sum of x acting on xi, right? Partial xi at P, for what it's worth. I'm using your problem 5. Remember we learned that the components of the vector field are given by just evaluating the vector at the coordinate functions. So if I want a formula for the ith coordinate of x, I just take x and I evaluate in the ith coordinate function. That's it. By your homework problem, generalized to n dimensions. Excuse me. Yeah, n dimensions. I equals 1 to n. So that's what x looks like, you know. And oftentimes, instead of writing this, I'll just write. I don't typically write that. I typically am like a little bit lazier and just write x upper I, right? But understand that the formula for x upper I is what? If we wanted to calculate it, we just take x and let it act on the coordinate vector xi. I've had v instead of the big X for that before. Don't be distracted. Now, f, the function, well, we can write f also as what? It's y1 composed with f, y2 composed with f, y m composed with f. Those are the component functions, if you will, of the map. Now we don't usually write it like that, right? Our typical notation is just to write like f upper 1, f upper 2, f upper 3, right? But you could also look at it that way. This is f upper 1. This is f upper 2. Because remember how our coordinate worked? Like how did the coordinate function work? It takes in the point and it spits out. Yeah. So that's a self-fulfilling prophecy. I mean, that formula is fine. But great. So we define the differential of f at P to be the mapping from the tangent space at P to Rm to the tangent space at f of P of Rm as follows. All right, so how's it going to go? It is the sum j equals 1 to m of the differential at P of f j of x times partial y j f of p. But we could break this down further, right? Like what this really is the sum I equals 1 to n rather. This was supposed to be an m, as in mommy. So I equals 1 to n, sum j equals 1 to m. All right. And well, so I'm going to pull the xi out. And this would be partial f j partial xi. So I'm okay, I need to include one more. I'm sorry, let me not skip that step. There's a step you guys should see. This is dpfj acting on partial xi. But remember what we did last time? This is a function. The differential of a function acts on a vector. How does it work? Yeah, but I mean, last time we said that df acting on v is just v of f, remember? So applying that to the jth component function, this just becomes partial fj partial xi. This right here, and let me just take the liberty of writing the xi on the other side. I'm on a chalkboard here, so I'm going to have to erase and rewrite, okay? But like, let me rewrite it just a bit. So this is partial. I'm just changing the order of things to emphasize something. So this is the Jacobian of f. This is which is the row and which is the column index? The component function is the row index, right? Jth component function goes with the jth row of the Jacobian. So this is j sub f, j, I. I is the column. Now, I may be referencing something you don't know, but if we take the sum, j equals 1 to, or rather I equals 1 to n of that, what are we looking at here? This right here. That's like a matrix column product, right? That's the product of the Jacobian matrix with the column vector formed by the components of x. That's what we did over there. So anyway, this is what I was saying, is that the push forward is really programmed. I mean, it's really, well, energized, whatever you want to say. It put into motion with the formula for it, the real formula for it. It's in terms of the Jacobian matrix of the map. So really, don't be too deceived by it. It's really nothing more than the linearization, except instead of using standard basis vectors, we're using the partial derivatives for the basis of the domain and the partial derivatives for the basis of the range. And I don't know if you realize this or not, but you've actually already done a push forward. You might not have thought about this, but this will be my final example for today. But I think one very interesting example of the push forward is given to us by, if we look at the map, which f goes from, let's say, r with coordinates r theta to r with coordinates x, y. Right. So what's the formula I'm thinking of? F of r theta equal to what? Coordinate change map, yeah?
Yeah, it's r sine theta or cosine theta, y sine theta.
Right. So actually, when you work through the details of the push forward, in some sense, it's like this. Partial r is, well, it's partial x, partial r, partial x, plus partial y, partial r, partial y. This actually describes the push forward. I mean, this is, you work this out, we get what? Cosine theta, partial x, plus sine theta, partial y. And I'll just tell you this, if you actually slug through the definition of push forward, you can prove that the push forward of the partial r map is equal to cosine theta partial x plus sine theta partial y. Now that's not a proper formula yet, because the push forward really should be stated in terms of the coordinate functions of the range, right? And the range here, as I've stated, is xy space, right? So I shouldn't really leave sine theta and cosine theta like that. To be fair, I should rewrite them as what? How about x over the square root of x squared plus y squared? And then y over the square root of x squared plus y squared, because that's how we write sine and cosine in terms of x and y, yeah? But there you go. That's in fact the push forward of the partial r. And the push forward of partial theta would be much the same. You've probably done calculations like this in your Calculus 3 homework, but you've thought of it in a different way, right? Like if we want to take a differential equation and we want to change coordinates on it, right? If you have a differential equation in terms of x, y, and you want to restate it in terms of partial r and partial theta, right? Then you need these kind of like formulas to change from one partial derivative to another. If you want to really see the man behind the curtain, what's going on there is you're using a push forward of the coordinate map. You're pushing forward the derivatives with respect to one coordinate system to derivatives with respect to the other coordinate system. So push forward, it does a lot of different things. One thing it does is describe how derivatives change under coordinate map. But it does more than that. See, it doesn't have to just be equidimensional domain and range. It can also push vectors in a two-dimensional domain to corresponding vectors in a three-dimensional domain. And anyway, the push forward is something that's going to be something we use because as we study spaces in this course, we might want to like push forward an object from one space to another. It's a very important idea because the push forward allows us to take vectors on something we know. If we've just got a map from one space to another, we can push forward the vectors over to the other space using the push forward. It's a very useful idea. So there's also something called a pullback, and we'll talk about that next time probably. So pullback lets you to take differential forms from the range and move them back to the domain. But anyway, I shut up. 4 hours